In this first module of the course, we're going to explore some of the fundamentals of music technology, the way sound works, the way we represent it digitally, the way we convert it between different representations. In this very first video, we're going to talk about the very basics of sound waves, the way we look at them visually in terms of waveforms, the way they act as functions, and how sine waves are a particularly important function to think of with sound waves. And three important properties of them: amplitude, frequency, and phase. So let's get started. This is a waveform. You've all probably seen something like this before. It's a basic way of representing sound visually. What we have here is, on our x-axis, we have time. Then on our y-axis, we have amplitude. I'll explain more about amplitude in just a second. One important thing to note about this is that it's actually a function. For each x value we have, each time value, we have exactly one and only one amplitude value that corresponds to it. Before I go on here, I want to go into a program called Reaper that we'll be using a lot in this course and actually record a sound for you so you can see what its waveform looks like. Welcome to Survey of Music Technology. So you can see the waveform that showed up here, and you can see how the amplitude is going up and down over time. And you can actually kind of make out the individual words, where you see where it stops between words and where there are different emphases or changes in phonemes that I was pronouncing, and so on and so forth, and the silence at the beginning and the end when I wasn't really talking at all. So like I said, waveforms like this are functions, and so we could think about them as actually being mathematical functions. So what would make a good function for a waveform? We could think of something like, for example, y equals x squared. That might make an interesting function. But there's a little problem with that, because as my time increased on my time axis, my amplitude would eventually kind of go up, and off to infinity. That's probably not something that we want. Instead, we want something where the amplitude is always going to stay within a particular range, between a particular high and low. And so a better choice might be something like a periodic function, like y equals sine of x, because then it'll go up and down over and over again. It'll always stay within a particular range. It turns out that sine waves are a very important function for us to think about. Here's a sine wave, and you can hear what it sounds like. And I want to talk about some of its properties now. The first one I want to talk about is amplitude. So this is the y-axis I've been talking about up till now. And it's going to go typically from -1 to +1. And then this horizontal line across the middle represents the 0 point. And so we can think about this as a lot of different things that amplitude is representing. We can think about it as a speaker cone that's pushing and pulling kind of back and forth to create sound waves. We can think about it as air molecules that are kind of pushing and pulling back and forth as a sound wave is propagating through space. We can think about it as our eardrum pushing and pulling back and forth in response to those sound waves. We can think about it as a violin string that's vibrating back and forth, and so on and so forth. But literally, it's this measure of kind of how much is something going back and forth. How much is it vibrating or pushing and pulling or something like that? And what is the magnitude of that change? And so we can think about these as individual values at particular moments in time. What is my amplitude value? You know, here it might be 0 or 1 or 0.5 or something like that. We can also think about it more generally in terms of the notion of an envelope. So in this example, there are individual moments where we can say, well, the amplitude at a particular time is this value. But there's also this larger trajectory. I can kind of trace this gradual crescendo, or this increase in the amplitude over time. So at the beginning, it's obviously 0, and then at the end, it's at about 0.5 is the peak of the amplitude. And so there's this gradual change that's also important to describe, and we can describe that in terms of envelope. an envelope of something is kind of this gradual change. So at first we're kind of multiplying all the values by 0, and then we're gradually increasing that number along this linear ramp here. So at the end we're kind of multiplying all the values by about 0.5. And envelope is a very important thing in terms of amplitude, and in fact in terms of a lot of other parameters in music that we can control gradually and gradually change them over time through a process like this. Just to show you in a little more detail what I'm talking about, if we go back to Reaper here, we can see here's a sine wave, and you can see at the very beginning here, it's actually fading in at the beginning, and this red curve here is showing the amplitude envelope. I can actually change that a little bit just by dragging with my mouse, so it happens more gradually or more suddenly, and you can see how the sine wave is changing in response to how I've changed that envelope. Another really important property of waves are their frequencies. And so if we look at this sine wave here, there's a couple of important terms to think of. The very top point of the sine wave is called its peak. And the very bottom point here is called its trough. And so if we measure the distance from one peak to the next peak, that is called cycle. And so frequency is simply measured as the number of these cycles per second. And it is measured in a unit called hertz, which is usually abbreviated as Hz. So for instance, the sine wave I'm about to play you in this example here is at 440 hertz, 440 cycles per second. And 440 is actually a standard that's used, for instance, in tuning. It maps to a particular A that orchestras will use to tune to. So here's the 440 hertz sine wave. So what frequencies can we as human beings actually hear? What you usually see people say is it's from about 20 hertz up to about 20,000 hertz. Here's a chirp sound that sweeps from 20 hertz all the way up to 20,000 hertz so that you can hear that full range of human hearing. It's important that you understand that this is all approximate, and I want to delve into that in a little bit more depth to explain exactly what I mean. First of all, when we're at the low end of that spectrum, when we get below 20 hertz, we might very well still hear the sound, but that's when it stops sounding like a pitch to us and it starts sounding more like rhythm. So as an example here, I want to play you something at 10 hertz, which is actually a sawtooth wave. And what you'll hear here is that it's not going to sound anymore like a pitch, but it's going to sound like rhythm. So you can hear 10 times a second that beating going, da 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 da, and so on. So that's what happens on the low end of the spectrum. On the high end, the 20,000 hertz end, different people may be able to hear up to different levels. Particularly as we get older, we have a harder and harder time hearing those really high frequencies. My favorite illustration of this comes out of a security company in the UK about 7 or 8 years ago that developed a very high sound, about 17,000 hertz, that it marketed to stores to play on speakers outside the stores. The idea was that people over the age of 30 were not supposed to be able to hear it, but the teenagers at the stores didn't really want kind of hanging around, would hear it and find it extremely annoying and would therefore leave. This had some moderate success, I believe, in that application, but where it really took off was when some teenagers decided that they could use that sound in another context, as a cell phone ringtone, because they weren't allowed to use their phones in class. And they set it up so that the 17,000 hertz tone would play whenever they received a text message. So that way they could hear when text messages were arriving and kind of surreptitiously check their phones in class. But their teacher, who presumably was over the age of 30, was unable to hear the sound at all and had no idea that these things were happening in the classroom. For fun, I went ahead and made a 17,000 hertz a sine tone here that I thought I would play for you to see if you're able to hear it or not. Hear that, that either means you're pretty young or you've kept really good care of your ears over the years, and you're very lucky that you're still able to hear it. And just one final note here is that some animals have different ranges of hearing than we as humans do. Dogs, for instance, can hear as high as 40,000 or sometimes even 60,000 hertz. So that's why when you see a dog whistle, it's just making a tone that's higher than 20,000 hertz, but falls well within the range of dog hearing. I want to move on now and talk about one more property of, I want to talk about one more important property of sound, which is phase. Phase really relates to the offset between two waveforms and how they relate to each other. So these two sine waves are perfectly in phase. And the reason I say that they're in phase is that every peak lines up with every peak. Every trough lines up with every trough, and so on and so forth throughout. And so when we play these back together, it's actually really just going to sound like one louder sine wave. So these are my two sine waves. They're perfectly in phase. I play them, and it's just a loud sine wave. If I play them individually, I hear one, and I hear the other. I hear them together, and it's just two sine waves. Now, on the other hand, we can have things that are perfectly out of phase with each other, and we get a process called phase cancellation. So these are perfectly out of phase. And what I mean by that is that all the peaks in the first one line up with all the troughs in the second one. All the troughs in the first one line up with the peaks of the second one. And so if we go and we listen to this, I can listen to the first one. It sounds just like a sine wave. I can listen to the second one. It sounds just like a sine wave. But I play them together, and we get a little surprise. Absolutely nothing. Because at every moment in time, these two add up. Their two amplitude values add up to equal 0. So they've effectively canceled each other out. That's why we talk about phase cancellation. There's something in between these two which can happen called beating, which is when we have two sounds that are at slightly different frequencies from each other. So here's one at 400 hertz. I apologize, this one is at 440 hertz. It's the same one we've been listening to. And this next one is at 441 hertz. So they're 1 hertz apart. 440, and this is 441. They're so close in frequency. But over time, because one is slightly faster than the other, they're going to go through patterns of being completely in phase with each other. So they're adding up to make something just higher in amplitude, and being completely out of phase with each other, in which case they're going to cancel each other out. So here they're completely out of phase. Here they're completely in phase, completely out of phase, completely in phase, and so on and so forth. And so these patterns are going to generate their own unique sounds. We're going to hear a pulse once a second, which is called beating. And this is actually a phenomenon that musicians often use when they're playing real instruments to help them tune. If they hear that beating, they know that they're a little bit out of tune with each other. And the more that beating slows down, so if it happens once a second, it's beats at 1 hertz, they know that they're 1 hertz apart from each other. If it's at 5 times a second, they know they're 5 hertz apart from each other, and so on and so forth. And then when it disappears entirely, they know that they're completely in tune. So to review what we've covered in this video, we've talked about waveforms and thinking about them as functions, and sine waves is a good example of that. we talked about three important properties of waveforms: amplitude, frequency, and phase. In the next video, we're going to ask another question, which is whether these notions of amplitude, frequency, and phase are enough to describe how we hear sound, or if we need to think about some other things as well to describe the difference between what we might see on a waveform and what we might actually hear.